Sometime around 400 BC, a philosopher named Democritus had this idea that if you took something, say a sugar cube, and you cut it in half again and again and again, you'd end up with really tiny little particles of sugar. And eventually you'd reach the point where you couldn't divide it any further. And Democritus labeled these building blocks that make up everything as atomos, which means indivisible. The whole idea that all matter is composed of atoms has been around for a really long time. Fast forward about 2,000 years, and now that we have more sophisticated balances, scientists can study elements and compounds quantitatively by measuring things. And some laws that came from all of this experimentation are, first of all, the law of conservation of mass, which states that mass is neither created nor destroyed during ordinary chemical reactions or physical changes. It just gets moved around during the formation of different compounds. And the law of definite proportions, which states that a chemical compound contains the same elements in the same proportion, no matter what. Which means that a water molecule will always consist of one oxygen and two hydrogen atoms. John Dalton summed up the view of the day with all of this experimentation with his atomic theory, and he stated that all matter is composed of extremely small particles called atoms, and he was right about that. The second part of Dalton's atomic theory states that atoms of a given element, say gold, are identical in size, mass, and other properties, and that atoms of different elements have different sizes, mass, and other properties. Well, he was partially right. All atoms of gold will have the same properties, but they might vary in mass. And we'll find out more about that when we start to talk about isotopes. The third tenet of Dalton's atomic theory states that atoms cannot be subdivided, created, or destroyed. Well, again, we've learned a little bit differently that atoms can be ripped apart by nuclear fission. So we could qualify that statement by saying by normal chemical means. And atoms of different elements combine in simple whole number ratios to form chemical compounds, and that's true. And finally, in chemical reactions, atoms are combined, separated, or rearranged. Also true. So not only is water formed by the bonding of one oxygen atom to two hydrogen atoms, making that formula be in the same proportion of H2O every single time, but also the mass of that oxygen atom is going to be a constant, as is the mass of those hydrogen atoms. So the mass of the water molecule is always going to be the same, as the atoms are always present in the same proportion. Nuclear fission can happen as a result of a nuclear reaction in the case where the nucleus of an atom is bombarded by another particle and splits up into smaller particles. Or it can happen as a result of radioactive decay, which just naturally happens to certain elements. But either way, this process releases a huge amount of energy. And those new particles that are formed now no longer have the same properties of the original atom. So now our definition of an atom is the smallest particle of an element that retains the chemical properties of that element. And all atoms are made of basically two regions: the nucleus, where you find the protons and the neutrons, and the area outside of the nucleus, the electron cloud, where you'll find the electrons. Collectively, we would refer to protons, neutrons, and electrons as subatomic particles. And we know this thanks to the hard work and experimentation of three really important physicists: J.J. Thomson, Robert Millikan, and Ernest Rutherford. J.J. Thomson is credited with the discovery of the electron, and he did this by using a piece of equipment known as a cathode ray tube. Now, cathode tubes used to be used in TVs, and that was how the picture was sent to the TV screen. Thomson's apparatus looks something like this. He had an evacuated glass tube, and then connected at one end was the anode, or a positive electrical current flowed into the system. The cathode, or the negative end, where the electric field moved out, or the negative end, and two metal plates that you can't really see on here, one up here that was positively charged and one down on the bottom that was negatively charged. And when connected to a battery, a beam of particles was formed, which was attracted to that positive metal plate. And since the opposites attract, the charge on that beam had to be a negative charge. And from his experiments, he was able to prove the existence of particles that were negatively charged and also their relative masses. And we now know that the mass of an electron relative to the mass of protons and neutrons is very, very small. Robert Millikan was a physicist that built on the work of Thomson. In his experiments, he measured the charge of electrons. By spraying oil in tiny droplets, Millikan used their density, the density of the oil, and calculated the gravitational and buoyant forces from the radii of those oil droplets. And using an electric field, he was able to determine the charge of the electrons in those oil droplets. Now, our accepted value of the charge of an electron is 1.602 times 10 to the negative 19th coulombs. And finally, we have Ernest Rutherford. His experiment is known as the gold foil experiment. And his apparatus consisted of a type of gun that shot out alpha particles. And alpha particles are made up of protons and neutrons, so they have a positive charge, which he shot at a piece of gold foil, really thin piece of gold. And the whole system was surrounded by this lead shield, which basically kept everything together. And what he found was that as he shot those positively charged particles at the piece of gold foil, was that most of them went right through the foil and hit the lead shield on the other side. But every now and again, those positively charged particles would hit something in that gold foil that would deflect it, and they would bounce back in the opposite direction. So there had to be something in that gold foil that was causing these positively charged particles to be repelled back in the other direction, which means they had to also have had a positive charge because like charges repel. And so from this, he deduced that atoms must be made of, first of all, mostly space to allow most of those particles to go through, but somewhere in that space there must be some sort of a dense area with a positive charge that caused those alpha particles to be deflected. And we now know that to be the nucleus, and the dense area of the atoms to be the nucleus, and the positively charged subatomic particles are protons. And so now our model of the atom shows a central area, the nucleus, where the protons and the neutrons are located. And protons, of course, have a positive charge. And neutrons, being neutral, have no charge. And outside of the nuclear area, we have the electrons, which have a negative charge. Most of the mass of the atom is here in the nucleus. This is a dense area that's positively charged. Remember that we said that the relative masses of protons and neutrons was much greater than the relative mass of the electrons. And this is really important because we know that protons, or the number of protons that an atom has, tells us exactly what that atom is. And the arrangement of the electrons in an atom tells us how that element is going to react. So now we've learned about the basic structure of an atom and how that basic structure was determined by experimentation. And we know that atoms are really, really small in size. And we know how they combine to form compounds. The next phase that we're going to move into is looking how atoms of a particular element might be different. And that's where we'll move on to into the next section. And I hope this has been helpful.